Hello and welcome to my lecture about bending members. In this session, we're talking about the moment resistance laterally unsupported member, especially single symmetric member or monosymmetric members. It is on class 13.6 of the code. Singly symmetric members. So first we need to know what members are called singly symmetric members. For example, if you have an I-beam which the bottom flange and the top flange are not in the same size, we call them singly symmetric members. For singly symmetric members, for class 1, 2, or 3, about I sections and T sections, lateral torsional buckling strength shall be checked separately for each flange that experiences compression under factored load at any point along its unbraced lengths. As follows, we're going to talk about that. And except those sections shall not yield under service load. Because if your section yielded under the service load, your lateral torsional buckling will be reduced and your resistance to lateral torsional buckling will be reduced. Okay, when the ultimate moment, or we can say the elastic lateral torsional buckling moment is bigger than MYR, resistance moment will be calculating using this formula. And as you remember, for class 1 and 2, upper bound is phi times M plastic. But here, first of all, in this formula, you have to say what is MU and what is MYR. MU for singly supported member is slightly different, as you can see in this formula. Now we're going to discuss about this formula. Okay. MU, we're defining a new parameter omega 3, beta x, and we have to calculate CW for this. Or if there is a section in the code, we can just read the CW from the code. Okay, beta x is asymmetry parameter for singly symmetric beam, which calculated like this. And IYC is the moment of inertia of the compression flange about the y-axis, and IYT is the moment of inertia of the flange about the tension flange about the y-axis. So by having these, so we know that what is Ix and what is Iy, what is IYC and what is IYT, so we can calculate CW and calculate beta x. By calculating CW and beta x, we can calculate this formula, except we need omega 3 too. For calculating omega 3, when a singly symmetric beam are in single curvature, when they are in single curvature, so it means that, consider this simply supported beam. This member is in a single curvature. So for single curvatures, omega 3 is equal to omega 2 for beams with 2 flanges, not for T sections, and 1 for T sections. In all other cases, there is a formula to modify omega 2, as you can see here, and be careful, it should be lower than 1 for T sections. The other parameter we need to talk about here is MYR. MYR is the yielding moment at y direction, factor 75%. As you can see here, it's My in y direction and 0.75 for the factor. The next parameter in this formula is LYR. LYR is length L obtained by setting mu equal to MYR. So mu is this formula. We want to put that equal to MYR, so it's no longer mu. So, and this L will be LYR, and this one will be LYR2. So if we solve this equation, we can find LYR. But probably solving this equation is a little bit hard or needs a professional calculator. But you can do it as by trial and error, put a, for example, initial value for LYR and get MYR, and change that initial value until you get the MYR close to the actual MYR. The other parameter in this formula is LU. LU is equal to this formula, where you can find RT here. In this formula, HC is depth of the web in compression, BC is width of compression flange, TC is thickness of the compression flange. So now you're able to calculate the resistance moment. Okay, resistance moment is in this formula, and again, be careful that the upper bound is plastic moment. Except for class 3 section, as well as class 1 and 2 T section, where at any point within the umbrage segment, the stem tip in compression, where MP is replaced with MY. So be careful that we said for class 1, 2, 3, I section, T section, we'll use this formula. But for class 1 and 2, it's MP. But be careful, you have to change all the MPs to MY for class 3. So actually, this is formula for class 3. We talked about the mu bigger than MYR, but what happened when mu is lower than MYR? So the resistance moment will be equal to phi times mu. For other singly symmetric shape, you have to use a rational method, and code didn't specify any method for you. And when you have biaxial moments, for biaxial moment, you're using this one. So when we have the factored moment x and factored moment y acting on a section, this is the criteria for design. So factored moment over resistant moment in x direction plus factored moment over resistant moment over y direction should be lower than 1. Thank you for listening to this session. If you have any question, you can either comment or email me.